So I'm a geologist by training, and I work in the Earth and Environment Science Department. I'm a part-time research fellow looking at knowledge exchange within geothermal energy. And I work quite closely with Mads and with Cathy in the control department now. So, right, well, first up, what is geothermal energy? Geothermal energy is heat from the ground. That's all it is. So where does the heat come from? Well, it's either left over from when the Earth was formed, pretty hot in the middle, 5,000 degrees C, 2,200 in the outer core, and that heat basically works its way outwards to the surface where we all live. Secondly, radioactive decay. Certain radioactive minerals provide heat, and that again works from the middle outwards. And also in the top, say the 10 metres of soil and sediment that we have, it's heated by the sun. So basically I've got there, heat is carried by fluid underground. So geothermal energy is basically tapping into that fluid and using it for renewable energy. Okay, so this is the University of Manchester's annual heat profile. So, does this have a... No pointer. So, we can see on the left here, that's our heating profile. I'm not going to talk much about cooling today, but we also have cooling demands. So we can see there, basically, we come through winter into summer and then out again. The demand, the annual heating peak is somewhere between 30 and 40. We're not trying to engineer things to be, right up here. We're basically looking for baseload heat. So the annual heating demand we have is about 90 gigawatt hours per year across the university buildings. So how much heat do we need? A lot. So all that heating at the moment in the university comes via natural gas. We have gas boilers which heat the water up and send it around district heating networks around the university. So if we're going to, as we've committed to, stop using fossil fuels for our heating, become more sustainable, what does any other heating solution have to do? So basically it has to provide constant heat regardless of whether the wind's blowing or the sun's shining. We need to be able to heat several large buildings. We have lots of large buildings around the town. It basically needs to be locally available. We can't transport heat very far, very cheaply. So if we think about the campus, it's fairly compact, but Greater Manchester or the country, it needs to be locally available. It needs to have a relatively small footprint. It's an urban location, there's not a lot of space. So it needs to have a relatively small footprint. It needs to emit significantly less CO2 compared to natural gas, otherwise what's the point? And not to cause excess grid congestion in the electricity grid. So this is the politician's view. I pulled this off LinkedIn yesterday. I just visited a geothermal project. Dan Jorgens is very excited about this. You just get heat from the ground, you just pump it up and use it, and it's cheap and it's safe. It's got huge potential. So somebody's taken him to a geothermal system which works really well. So yeah, but actually we all live in the real world, and we know that it's a multi-year process of geoscience, engineering, town planning, law, economics, community engagement, and all that sort of stuff. Taking somewhere 2 is unbelievably optimistic, but somewhere between 2 and 10. If you look at geothermal projects in Cornwall, they always seem to be a month away from delivering the first geothermal energy, and they've been going for maybe 20 years. So it's a long process. It would be nice, though, having said that, for some politicians in the UK to be as excited as Dan is about it. So how does it work? Well, basically we have 2 wells. One well pumps it up and one well pumps it down. Very simple. We call this a doublet. And a doublet, that is the production well there on the left. As you can see, it's basically very, very small footprint indeed. Just, about where these chairs are. Essentially, the final completion. That pipe is a hot water pipe. If you touch that, it'd be very warm. Goes into a heat exchanger. The heat exchanger takes it into a different clean water circuit, which then goes around the heat of the buildings. So the heat exchangers there, you can see there. Now, the important thing is, the deeper you go in the earth, everybody knows this, the deeper you go in the earth, the hotter it gets. We've all seen the films. In the shallow, we're looking at around about 10 degrees C. As we get deeper, we can be looking at greater than 60. 60 is about the the sort of limit, but what you need, you can use it directly. You don't need a heat pump, so we don't need extra electricity. In the shallow systems, we need a heat pump to boost the temperature so that it's usable. Now, so we can have doublets, and then what we're drilling into here are rocks which store water, which we call aquifers or reservoirs. Yeah, so they can be different types of rock. So this example I'm showing here is the production well, and the heat exchangers are from a geothermal greenhouse in Holland. So this guy, Tony Amelan, has a load of greenhouses full of plants grown in Costa Rica, which he sells to garden centres in the UK and abroad. So, is it doable? Well, maybe. We've got it wouldn't be a first of a kind project. We've got TU Delft there, quite happily engaged in a geothermal project. University of York have just received, 35 million quid to investigate geothermal energy in York. University of Leeds, just down the road, have a shallow geothermal energy system, which is due to come on stream, is working quite well. Newcastle University, less successful. They didn't get a lot out of their boreholes, and I'll talk about that a bit later. University of Warwick. So, we're in some fairly distinguished company here, and it's not just in the UK, this is in New York. So, perhaps more importantly for us is there's the University Hospital, the NHS Foundation Trust in Wythenshawe, are also planning a geothermal project to provide heating for the hospital as well. So, there's a lot of talk, and there's some action, but not massive amounts of action. We're lacking, I'll talk about that. So basically what we need to know, for it to work here in Manchester, the heat below our feet, where we're standing, are there any suitable rock types? Well, what do we mean by suitable? I'll talk about that. How do we find this out? Are the rocks extensive enough? Can they hold enough water for us to use for 20, 30 years? Do they have a suitable area and thickness? And why does this matter? Are there rocks at a suitable temperature? How deep do we have to go to get to 50 degrees C or 70 degrees C? And are they permeable? Can we get water out of them? And equally importantly, can we get water back into them? Because in a doublet we need to come up, take the heat, and then it needs to go back down. So, summary, how deep, how thick, how hot, how productive? That's what we need to know. So what's below our feet here? As geologists, we spend a lot of time thinking about what's below us. Normal people just walk around wondering what they're going to have for their tea. But we walk around thinking, I wonder what the rocks are like below my feet. So for geothermal energy to be used, we need to understand the subsurface. We're going to use a subsurface, we need to understand it. To understand it, you need geologists. So basically, sediments are deposited, usually in a sea. They get buried, and then we build up a vertical column of what we call stratigraphy, with different types of rocks in it. The oldest ones are at the bottom, obviously, and the youngest ones are at the top. So as conditions change, we get different types of rocks. Different types of rocks have different types of rock property. Some can hold water, some can't, some act as a seal, some we can mine for salt to put on the road. So in Manchester itself, I've put some little stars down there. We're looking at deep time. So we're going from about 358 million years ago to about 250 million years ago. And we go across warm, shallow seas, Carboniferous limestone, then we've got the coal measures, we've got the Millstone grit, we've got sandstones in the Permian, which are desert, semi-arid, hot seasonal rain. So, as geologists, what we do is we go, okay, well, how does the pattern of these rocks vary underneath? And I've put a little, we're all familiar with Ordnance Survey, so we draw a contour map, we know we're going downhill into a valley, we're going uphill onto a mountain. We just draw the same maps for underground. So here we're going from minus 151, which means 151 metres above sea level, down to about 2 kilometres. And everything's going downhill, southwards, towards Knutsford. Geologically, not just generally. So what we do is we can make a little cross-section so we can see that the polyhurst sandstone, which I've raised there, is dipping downwards and going to greater depths underneath Cheshire. So we can also make thickness maps so we see where it's thicker. Thick is important because if you're trying to get water out of an aquifer, thicker is better. It's got more water, so you can access more water, you get more water out. So Cecil Street car park I've highlighted here, that's one of the few places really around the university which is big enough to get a drill rig in. So, so they've highlighted that. And I'll just skip through the other ones. This is the millstone grit. We can see we're getting a lot deeper here. We're going down in the stratigraphy. So it's about 1,600 metres. Carboniferous limestone is about 2.5 kilometres deep. So how hot is it going to be down there? Well, what we do, as geologists, one of the fairly standard things you do is you measure the temperature at the bottom of every hole that you drill. So if you measure the temperature of every hole you drill, we've got this little graph here, which is depth across the top and temperature down the side. So what we can see is that, you know, unless you're on top of a volcano, then the temperature is fairly linear. So we know the surface temperature is about 10, seems optimistic today, but at 1 kilometre it's going to be 38 degrees, 2 kilometres 66. So, you know, if you want a nice bath, 1 kilometre. If you want to pasteurise some milk, 2 kilometres. So you can use the heat for different things depending on the temperature. So if we know the depth, we've mapped the depth, we can kind of work out the temperature. And then we need to know, well, how do the rocks deliver water? So we've got basically two types. This is, you know, an oversimplification, obviously, but they either act like a sponge, so they've got space to hold water within them, or this shattered pane of glass. Now, in the pane of glass, all the individual pieces themselves, you know, if you tipped a pint of water on it, it wouldn't go through the pieces themselves, but it would find its way through the cracks. So these are the two sort of end members. They're either fractured like this, or they're porous like a sponge. That's a spongy rock, and that's a fractured rock. You know, a core that's been taken from a well. We're looking at about 2,100 metres there. So we can see that these fractures occur in the rock at depth. Okay? So, I apologise for this now. Geologists don't really do sums, but even I can multiply three numbers together. So, in Germany, I've plotted the flow rate of geothermal systems in Germany here, and there is a wide range there. We're going from about 18 to, you know, over 120. So as an example, I've just done a little calculation. Obviously, the water carries the heat. The more water you bring out, the more heat you bring out. And the hotter the water is, the more temperature you can take out of it. So if you've got higher flow rates, you're taking more temperature out, you get higher power, and that's what we're after. So remember that in Manchester we need about 30 to 40 megawatts. So one doubler in Germany at those rates would produce about 16.8 megawatts. Now, if you wanted just to heat a house, a ground source heat pump in a house, you need about 10 kilowatts. So you can see that's about 1,680 times less. So shallow systems can deliver high flow rates, but because they are cooler, you won't get as much power out of them. So, how much power? Now, I should have put this up front. Now, there has never been, I would say, in my experience, a successful geothermal project anywhere in the world that doesn't have a really strong public engagement. GSNI are the Geological Survey Northern Ireland. The ones on the bottom left are from Cornwall. This is University of York. Up in the top here, we've got a geothermal forum. And we've got engagement with classrooms. We put seismometers in. This is also from Cornwall. So there's a huge aspect of this work, which arguably I should have put that first. I think that's the most important thing. Now, can it be done at scale? We talked about scale this morning. Now, this is Greater Manchester. So what I've done here is I've put at the same scale the city of Munich on top. And Germany, for various, you know, geopolitical reasons, trying to get off Russian gas, they've stopped burning coal, and they've got rid of nuclear. I've gone quite big for geothermal energy, and so they have a couple of still fossil fuel-powered CHPs, combined heat and power plants. But I mean, it is possible to do it at scale. So by 2040, they're looking at 400 megawatts rather than 40 megawatts, and the whole city being covered by geothermal district heating systems. So, you know, it's all looking good until I tell you what can go wrong. Now, this group of people, the International Finance Corporation, quite rightly focus on what can go wrong because it's their money usually is spending. So we can have inadequate reservoir temperature. It can't be maybe it's not as hot as you think it's going to be. In Manchester, I think we've probably got the opposite, because the coal measures seem to act as a sort of thermal blanket. So I think it's actually probably hotter than we think it's going to be by just measuring the average gradient. We can have inadequate well delivery. Now, this is a big one. I think this is the main problem we've got here. How are we going to get the water out? Do we know we can get water out, and do we know we can get it back in? And then on suitable water chemistry, you can see the corrosion and the scaling in these pumps. Now, for Munich, one of the big problems here is that you have high investment costs and a long depreciation period. So, when accountants get hold of this stuff, they don't think about the social programs and all that sort of stuff. They just want to know how much it's going to cost. So, and how it compares to just having gas boilers. Okay, so there's significant local differences in terms of exploration risk. If we drill a whole geothermal system in Wythenshawe Hospital, it works fine. We don't really know whether it's going to be fine somewhere else. Doesn't mean that if it works in one place, it's going to work everywhere. So there's local differences in the geology. And then also last one, again a big one, microseismic events, usually associated with injection rather than production. So again, that's something to think about. So to wrap up, how can we heat campus in the wider region without burning fossil fuels? Well, you're kind of stuck. Fossil fuels do everything. So how are we going to do a large user, a large power requirement for the university if you're not using geothermal energy? I mean, I'm not trying to sell it to anyone, but what I'm saying is that, you can get heat from a sewer or you can get it from somewhere, but your options are quite limited. Now, shallow systems are less risky because obviously the shallower things are, the more we know about them, there's more holes in there, and we've got more tests. Do we know enough to confidently predict the key factors, temperature? I'd say no at the moment, not really. So our little project, we're just trying to understand the geology and how we can de-risk these sort of features. And what else could we do to increase the probability of success? So that's it. Thanks.
Thanks so much. Will this work? It will. Perfect. Good afternoon. My name is Alexandra Barrueta, and I am one of the research assistants on what I think is very exciting new interdisciplinary research project that's on exploring community-led renewables. So I am going to talk about the project today. I'm going to talk about the potential, but mainly I'm going to talk about interdisciplinarity because I think this represents it perfectly and is probably what I'm most excited about. But I also have ADHD, so I'm literally like walking interdisciplinarity. So we are working with Manchester Urban Institute, the Tyndall Centre. We're working with the Institute of Innovation Research based at the business school. So we've got a little bit of everything. Before I tell you about the project, I need to tell you about how the project was born and what we're actually studying very, very briefly. And we are looking at core. So core actually started in large part due to sustainable futures. 2 years ago I gave a different talk, a very, very different talk about local solutions to net zero transitions. And after this talk, a man named Mike Franks approached me and asked to have coffee. Mike is here today, and he runs the Manchester Climate Alliance. He then introduced me to another Mike who ran Planet Hydrogen. And the three of us together decided, hey, there is a problem in Greater Manchester around heating, how can we solve it? So we established CORE. CORE is a community benefit society that essentially helps communities that suffer from fuel poverty get funding, grants, and information about renewable energy. And we went in guns blazing, we got funding for it, we thought it'd be as easy as all my projects in Mexico. It was not. It's incredibly difficult, and we genuinely could not figure out why. So we have 3 sites, and they're great sites, and they're very, I think, exemplary of Greater Manchester. We have a site in the north, based in a community centre called the Apostles near Miles Platting. We have a centre you might be familiar with, it's the Victoria Baths, very, very near the university, and then we've got a community centre in Wythenshawe called Dandelion. These 3 places are what we call community hubs. Now, we're not focusing on private homes quite yet because one of the barriers of entry really was misinformation and distrust. So we thought, okay, let's start with community hubs. Let's start with these spaces that people are using, that we need to heat, and show that we can heat these spaces, we can do it well, it's safe, it's sustainable, and maybe then this will kind of permeate out. And people will be more interested in using these technologies for their home. But the amount of issues that started emerging, we were trying to go in and do this, and just people weren't interested. We went to schools and they said, we don't really want this. We don't really trust the technology. We don't believe in this. It's not really a priority. And as scientists, we were very confused. And then one day, Karen Lucas, who you might be familiar with, said, hey, there's a project here. Let's all get together and let's talk about it. But not just the social scientists. Let's get the engineers in the room. Let's get the economists. Let's get, the people that are studying impact. And that's what we did. And so we created a research team. This is all of us. And we all specialize in different things. And that's what I'm going to talk about today. I'm going to talk about how you get a group of people that have completely different priorities, that are thinking of completely different things, that want different data, different answers, and how we are, at this point, trying to deliver on a project. So, as I said, interdisciplinarity. This project examines whether co-designing renewable energy initiatives fosters stakeholder ownership. So, first barrier of entry, they don't want it. They're not interested. It's working. So how do we do it? Do we go top down? No, that hasn't worked. Historically, it has not worked. How do we get these communities involved? So as we just heard, you need to do community outreach. You need to actually be speaking to the people that are using these spaces. Our core components of our research project are mixed methods research. So we do have scientists from across different disciplines. We've got engineers that can do GIS-based techno-economic feasibility analysis. I am not an engineer, so it was very difficult for me to say that. I still don't fully know what it means, to be honest. We have quality community engagement and co-production. We have ownership model evaluation and business case development because we want these things to be replicable. And then obviously we want to apply for follow-on funding because this is important. We do need more renewable infrastructure across Greater Manchester. We need it across the whole world, really. I mean, I wish we could do more geothermal. And these are the challenges that we started to find. There was a talk-action dissonance that was perceived by these communities. That initial distrust, that initial hesitancy to actually even let us in or speak to us comes from years and years and years of people coming in, making huge and bold promises, and just leaving after they've collected the data or after they've gotten the publicity. And so they're just kind of left like, well, we keep getting promised these things, but nothing happens. Our community centers aren't actually heating. We can't actually work with them. And that's what we want. Insufficient financial support. So renewables, they get touted. They're very important. We have policy. But actually getting access to that money, if you're a small community center, is near impossible. For the most part, you have to be associated with some research group or an installation group or an investing group. And oftentimes people don't know about these funding calls or genuinely is very intimidating to apply for them. You're looking at a 10-page application that asks for science, that asks for data that you don't even have. It's difficult for us, and a lot of us do this for a living. A lack of revenue certainty mechanisms. So, okay, once we install it, how do we uphold it? How do we continue it? At the moment, the most popular community-led or community-owned renewable projects are top-down. So they are things like a subscription service, where you get solar panels installed in your home for free, and then you pay a subscription service, but you don't actually own that infrastructure, which means that any potential benefits from those infrastructure, they don't go to you, they go to investors. Who are the investors? I don't know. No idea. Or you have a wider call for a community-owned renewable project. There's quite a few in Greater Manchester, and they work really, really well, but it's an open call. Anybody can invest. It's also a really, really good tax benefit if you're above the threshold you guys have in the UK, which means that the people that are investing are the people that need those benefits, and it's very, very rarely people that actually live in the community and use the space. So we have the exact same problem. This is one of the main issues that we wanted to address with CORE. We wanted to see through grants and funding, how can we minimize that call for investment so that we can keep the majority of the infrastructure in the community it's actually serving. And this then has even more problems because long term, it's a massive infrastructure. Who's going to take care of it? How are they going to take care of it? Are there engineers? Do we pay for youths in the community to go to school, to study the infrastructure, and in return they take care of it? So all of these problems started coming up, as does whenever you have a project. You think you've solved one problem and 10 more pop up. We have limited knowledge and trust of extant renewables. The reality is that all we hear about is renewables. There's distrust on nuclear, there's distrust on solar, there's distrust of, it's not even a renewable, but people don't want 5G because the towers are ugly or they're emitting something. And so imagine coming in and saying, we're going to install solar and a heat pump. They've heard bad things, they've heard good things, they don't really know, they don't really understand. And we need to be able to communicate. This is what we think you should do, this is why. But at the end of the day, we can't just go in and say, you're doing this because we say so, because we're the scientists. And this is where community engagement comes in. And finally, as I said, the primary ownership models have been top down. This doesn't work. It's very white savior, it's very, we know what we're talking about, and they're never going to trust us if we do it this way. And there's not going to be that co-production element of it, which is so, so important for these kind of infrastructure transformation projects. So our project aims essentially are to deliver all of this, but mainly to discover what are the issues. Why have there been issues? Why is it not working? Why isn't this more popular? The money is out there to some extent. The technology is out there to some extent. The need is out there. And trust me, the people willing to do this are out there. Most of the community-led renewable energy projects in Greater Manchester are volunteer-led. These are people that have 9-to-5 jobs, and then after work they come and they try to run these initiatives to get community centers powered, and they don't get paid for it. So the willingness is there. The support from the government is there. We've spoken to GMCA, they want to help. We've spoken to the university, they want to help, but it is not being delivered, and that is the issue. So, what we discovered is that the first solution is interdisciplinarity. We need to have different people from different areas in the room. And not only, when I say interdisciplinary, I don't only mean economists and engineers. I mean, we need actual people from the sites. We need people that are going to be using these spaces to participate in these conversations. Hey, why do you want to heat this giant church building that you use as a community center? What do you actually want it for? Because if I just go in and guess, it's not going to be functional, it's not going to be used, and it's a massive waste of money. So one example is the Dandelion Community Centre. And this is kind of just to walk you through some of the struggles we've had with the project. Dandelion Community Centre is a church, but it's so much more than that. It is a community hub. So there are different groups that work from within the community centre. There is a food pantry. There is a men's mental health group that meets every week. There is a after-school children's group. There is a gardening club. There is a sensory room for neurodivergent children. There is a multi-faith room. There is a quiet room. There is free legal aid. There's free financial support. All of these things are available for free for anyone within the community. There's even a gym for elder people so that they can go and they can work out a little bit and they have that guidance. It's an incredible place, and it is an example of how we should be running community centers. It's freezing. It's a room about this big with huge windows, single glazed, and not really any heating other than old oil heating. So they're spending a fortune on heating, and honestly, it's just not sustainable for a community center like that. So we went in with engineers and we said, hey, what's feasible from the engineering perspective, from the math perspective, because I'm not good at math. And I said, okay, well, let's look at heat pumps. Let's look at solar. And there's massive, massive potential. But this isn't where it ended, because we actually had to speak to the people. Hey, do you mind if we have solar panels on the roof? Do you mind if we take up some space to install heat pumps? They might be a little bit loud. How is that going to affect your sensory room? How is this going to affect the usage? So it has to go hand in hand. We have to be asking more questions than just, is it practically feasible? Because what we are delivering is impact, but it's impact across a plethora of different areas. And so then I come to what we've discovered about working as a group of researchers that have different approaches, different priorities, different ways of communicating, And I think this has been the most difficult. And I mean, would you not agree? That translating between math and social impact is quite hard at times. So our key lessons that we've taken away from this project and from working through CORE with the communities is that it has to be community. And when I say community, I don't just mean where we're delivering. I mean the people that are on the project have to form a community. And you have to be communicating. And you have to find a way to translate these different priorities. And it was incredibly difficult because I wanted data on the business models. How are we doing this? How is it going to be successful? The people that we're delivering this to, so the owners or the volunteers or whoever really we're discussing the progress with, what they wanted was they wanted a replicable model, which, by the way, doesn't work. You can't just copy and paste something that works in Wythenshawe in Victoria Falls. It will not work. The second thing that we learned is how you communicate matters. If I go in and I say, hey, these are the megawatts that you're going to produce, okay, so what? Maybe someone cares about it, but Kay at Dandelion Community Centre, who's 70 years old and needs to go there so that she can have her morning coffees, does not care. And Edward, who's up in Miles Plotting, that goes for his gardening group and wants to come in and have his men's mental health group, again, does not care. So the way that we're communicating isn't necessarily going to be in numbers. It's going to be, hey, this is how we can help you. This is how we're going to heat this building. And this is the impact it's going to have. We're going to have volunteering groups. We're going to be able to hire local people from the community. Do you know anybody? We're also going to explain to you about this technology and why it's good for the environment. Because, hey, maybe we shouldn't be using fossil fuels anymore. We've learned that measuring impact is an exercise in respect and trust. Because while I might want to measure the impact of the economic measures that we impose, maybe the engineers in our group want to measure the impact of the actual technology or the infrastructure. And Joanna Barrow, one of the social scientists on our groups, wants to measure the impact on actual social change. And that's amazing, but we should be measuring all of these different impacts. And finally, we've learned to celebrate those differences in the communities and in our research group. Because while we might have butted heads in the beginning and we might have been really frustrated, I think at the end of the day, what it's done is it's really pushed us to get out of these little bubbles that we exist in and realize that there isn't a single one pathway to solve this problem. Just like there isn't a copy and paste solution to community-led renewable energy, there isn't a one copy paste solution to interdisciplinarity in groups. So we need to celebrate the differences in the communities because all three communities are vastly, vastly different. We thought they'd be similar. They have similar demographics. They're not. And this is what we're finding. We have to celebrate the differences within our research groups, and we have to celebrate the differences within the different opinions and thoughts. That being said, we're still trying to get renewables. So that's really it for me. Thank you.
Thanks very much, Alexandra.
Yeah, I would clap. So my name is Vidi. I'm a senior lecturer at the University of Manchester, electrical and electronic engineering. That's about the first slide that I think I know what I'm talking about, and everything afterwards is new to me as well. So I got an invite. Alice was really kind to say, "I'll come and join the conversation around sustainability," and I said yes first thing. Then realised I don't do anything with sustainability. I don't get to talk a lot really, so it's an opportunity for me. So I'll take it up anyway. So I put up some slides. I might be jumping between, but the conversation is around electrical networks. Okay, so I'm trying to bring maybe a correlation between sustainability and the electrical networks. My expertise is essentially around the asset. Okay, the electrical asset, high voltage assets, right? So the pylons that you see when you're on the motorway, the large substations that you see when you're coming into big cities, the kind of you see these kind of office spaces outside your houses and stuff, and they'll say don't enter substation transformers. So that's my expertise, and I work around accelerating new technologies, de-risking old ones, understanding how they fail. An example of that is your heat-throw transformer. Right, that's one kind of an asset. How do they fail? how do we extend life? The problem is not about failing, it's about actually making sure you know when it's going to fail so you don't need an outage. Like I said, the Heathrow is a big example. When the transformer did go off, what happened when you don't have an unplanned outage is you lose a lot more things on the network. They're all interconnected. The T-pylon, I don't know if you've seen this actually connects Hinkley Point C. I was one of the design engineers that was recruited by National Grid. So I effectively work as an academic, but also a consultant, so knowledge exchange fellow. So I could work for anything from 1 day to 2-3 years on a project, so I've got that flexibility. Quite a lot of projects, as you can see. I've worked on anything from wind turbine blades to generators in a ship. I actually got a fully paid cruise ship from the Bahamas to Florida to go look at the generators on a Disney cruise. I went on my own. And another academic. Quite strange when you walk into what is effectively Disney dream. Two blokes. But to be fair, actually, we were not the youngest on that. There was quite a lot. The Disney Club is quite a range from 90s to 9. So, but there's a lot in there, and I've done about 100 projects. Not just me, but with colleagues. So quite varied. But the networks is actually a very upcoming area. Everyone talks about electrification, right? Electrification. What does that actually mean? So I also work in UK's largest high voltage lab. So that is actually right opposite Sackville Street. It's like a right move picture. It never looks like that, right? Like the first picture that we took as soon as we moved in. There's actually someone injured in the corner here, usually, it's all over the place. But it's a very much used space. Okay, so what do? We test equipment that can go up to 400,000 volts. We can also do lighting in the lab. Okay, so the one that you see over there on the left-hand corner, that looks like a Lego machine, effectively does 2 million volts. So we can do up to 5-6 meters of a lightning bolt. Your network does get hit by lightning. And you have to make sure that the equipment can sustain that force, but at the same time does not go off. If you're sitting in a sandbar, which some of us do, for meetings, you can literally see the lab from it. Not now, because there's a lot of cardboard boxes in that window, but usually you can. Quite nice to see it after 4 o'clock when the lights are on. So yeah. So the electrical network. So I'm going to kind of talk about the electrical network. I'm going to ignore the kind of generation part for a second because not necessarily my area of expertise. But the electrical network itself is complex. Have overhead lines, cables attached by these substations, all interlinked to each other. The impact of one can have an impact on the other. It's crisscrossed across, right? I basically built this on AI. I asked it to put some cables in there, and it basically put the cables on the overhead line. I was like, that's wrong. That's wrong in its own to begin with, but if as a picture, that's great, because your generation is right next to the city, and your offshore farm is right next to the city. You can see the, your dam's right next to the city as well. So, shows you the AI. However, so I did say it is an oversimplified. That's what your network looks like. Okay, 3 zones, as done by NESO. Okay, the blue is run by National Grid. The yellow is run by Scottish Power. The top is South and Southern Energy, Scottish and Southern Energy. Okay, all of these guys operate at 400,000 volts, 400 kV. So the large conductors that you see on the motorway when you're driving down, they operate at 400,000 volts. Think about the voltage that you have, a couple of hundred at home, a couple of 100,000 over there. Okay, that's why they're all quite higher, okay, because you can't really contact them. You have to isolate them from the ground. I won't further complicate this by adding the distribution networks, Electricity Northwest or Scottish Power Northwest now, Northern Power Grid. So you've got the sub-network of that, those guys who actually connect your houses. Okay, this is the transmission network, and it's complicated as it is. Putting that aside, this is what's called the future grid. Okay, I don't know how many of you have heard something called the Great Grid Upgrade. Okay, National Grids are communicating that was putting a plug socket onto a bus stop. I was like, great, that's how you communicate it. So it's not great, we don't really communicate as well. There's about 26 projects, okay? And a significant amount of that is what you're looking at, the yellow, okay? the holistic network design. These are wind farms that bring in a ton of renewable power. Okay, all of them subsea cables. This is just a new network. It's about, I think, about in the next couple of years, about 100 billion. They're talking about next 10 to 30 years. I'm not even connecting the existing network. This is just a new network, which means we're building, upgrading, maintaining exactly at the same time. We are so used to turning on your switch when you go in. Take that out. Take that equation out, right? Not many of us actually seen power cuts in our lifetime. I grew up in India for a considerable part of my life. Power cuts were quite common. And we talk about distributed generation, we're talking about local, people having their own power supplies and not being connected to the grid. But people need to also understand we have such a big resilience on the network right now that we're used to. And we don't like losing that. Okay? So this network is actually of prime importance for us. It's security, it's affordability, or is it sustainability? All three actually. But what do you take into account? And also are traditional technologies of wires and cables enough for a resilient network? Okay? Can you keep building the same way that you do? Knowing that this has to run for another 100 years. Okay? So I typed in, just looking at sustainability, and the problem that you have is, some of these things, big transformers, like again, I use the word the heat one because everyone's heard of it. That transformer is called a grid transformer. It's pretty big. There's only a few places in the world that can manufacture it. The lead time for that is 60 months. So you place an order today for 2030 of what's on your catalogue today. What sort of innovation is going to happen? Why would anyone do an innovation? You're buying what I have right now. And also I have to ask myself a question. It's operating fine. You replace this in what, 3, 4, 5 years? Your grid's 60 to 70 years old. Talk about sustainability, right? And we try and extend life as well. So there's a lot of good things that happen on the network as well, but there is a challenge of actually introducing innovation. It's a big risk. The number of complaints that you get when you get a power cut is going to be massive, so you don't want to put something new. So there is quite a lot of inherent inertia. I'm trying to look at my time at the same time. I typed in electrical network and sustainability and all of this came up. Nothing about the grid. It was about renewables, distributed generation, AI tools, efficient houses, demand-side management, nothing about the actual network. You're not going to get electricity to your houses without it. Those overhead lines, those cables, those substations are very much key in actually making you a resilient network. So I'm going to step back and I'll kind of think like, so what am I going to concentrate on today? I'm going to concentrate on two things. Understanding sustainability from two aspects, renewable integration, so the equipment that's needed to connect those, and aging infrastructure. Those two assets. And how do you actually do this at a time when you're building more? Okay. So infrastructure at UK, it was about 60 years in life. I mean, we built in the 1920s, so we've actually gone past the 1920s. We've gone past the asset life, and we still need to build. It needs replacing. That's everything. And we're also trying to push for more. We're trying to kind of say, like, what is it that we can do? What can we get out of the existing assets? Upgrading of assets is difficult. It's metal, it's copper. Right? Transformer has a ton of copper. Overhead lines is aluminium. Cables, copper. Right? So we don't manufacture in the UK, not even to that level. So we know where they're coming from. They come from India, they come from China. So quite difficult in terms of sustainability. If you kind of think about how you build a network today, it's really difficult, the constraints. So you have an inherent use of what is a material or resource of not abundance, is it? So you have to understand, so what is the message that we have to build a maintain resilient network, at the same time update our equipment. But networks do try and find ways of introducing sustainability into their assets as well. It's not happening, but it's quite difficult. I'm going to put up a couple of projects. The one on the left-hand side is a project that we're doing at Manchester, where my couple of colleagues are working on what's called an SF6 replacement. SF6, sulfur hexafluoride, is a gas that's 25,000 more potent than carbon dioxide. And actually, it's how we distribute power underground. So if you go into London, you'll never see a wire on the top, or you'll never see a substation. That's because everything goes underground. When you put an electricity cable or a conductor underground, it needs to be enclosed within a test vessel like that, and it has SF6. 25,000 more potent. However, it's been used for about 90 years, 80 years. You replace that with a new one, you want to know if it's going to last 80 years, and that's difficult to find, and that's what we're doing at the university. We're looking at new cables, superconducting cables. Our project, a bit bonkers really, but there you go. Lots of data centers, so people like Microsoft and Google are very interested. Perfect. So actually you get a bit of investment. These are superconducting cables, which mean that you can deliver about 10 times a normal cable through a much smaller conduit. So you don't have to dig up a lot. That saves a lot of money. Compacting towers, so you've probably seen quite a lot of overhead lines like this. What we're trying to do is remodel them to a certain extent so you can use the actual tower, but operate it so you can actually push a lot more power in the same kind of existing bandwidth. And this allows you to actually use your existing asset and actually brings in sustainability as well. However, things take time. Assets, I don't like it. The TRL level does not mean much because just because it's reached at TRL level 9 does not mean it's going to go on the network. You need people to have that faith in actually putting something on the electrical network. So I like the word de-risking. So what people see is the top of the asset innovation. What they don't see is all the 4 things at the bottom. How do you standardize it? Because you don't want to just buy one piece of equipment that's unique and realize you can't put it back on again. You have to have your life cycle assessment of that. What happened in 10, 20, 30, 40 years? How do I asset management? What happens to the system? I'm putting a new piece of kit. If it goes bang, what happens to the rest of the network? And that's what happened. Again, like I said, I'm going back to that Heathrow one just because it's quite new. Heathrow is not just about the transformer going off. There was a systematic cascade of things that went through to it. Right? So the system level impact is very important on any kind of new asset you put on the HV network. Health and safety. And that's something that we are actually very keen on as well. And understanding the full life cycle on any kit is actually very key in the electrical networks. Very quick about sustainability. I've talked about the asset, but what about actually constructing the network? Okay? So I'm talking about burying a cable underground, the foundation for an overhead line, the actual digging up of soil to build a substation. All of that on the left-hand side is going to involve a significant amount of building. And this is not wires, this is not cables, this is moving mud, concrete. Okay? And I'll give you an example. I think it's quite interesting, right, how we talk about the society, how do we actually engage public. We've all heard about NIMBYs, not in my backyard. Okay? I'm going to show you an example of moving from an overhead line to a cable. So that is a report done by Mott MacDonald and the IAT to understand what electrical transmission technologies and their costs. Okay? In all of these, the copper or the metal kind of will stay the same. Okay, some of them overhead line will be a bit more expensive than a cable. But at the same rating, the overhead line costs about £50 million. Okay? Let's go to an underground cable. £500 million. Same power. The next one, almost you're nearing £1 billion. This is exactly the same power. So to do the same power, the prices are going up. And all that is digging, terminations, substations, actual civil works. So sustainability from a challenge and actually opportunities perspective is probably quite a lot in terms of the materials and building. And also you have to understand balancing the impact. Now, overhead line will have a higher visual impact, but it's a small material footprint because you can recycle most of it. It's all metal. In terms of cables, you're digging up soil 3-4 meters, which means that inherently there's a longer period of sustainability issues, and the cable's not that easily recyclable as well. But all of these have to be taken into account, and I don't think we do. There's a lot of miscommunication, people talking about not in the backyard. I heard a BBC interview where they interviewed someone and said, well, I don't know why they can't just put the cable around the country. And I was thinking, because at some point it has to come into your house. Just a motorway going all around, right? Do you know what I mean? I'm just like, how that, I mean, there's A roads, you know what I mean? How do you, that's like a motorway just going around and around in circles. See, there's a lot of misinformation out there, right? So I think we're trying to actually kind of say, listen, it is difficult to actually build this. So we're thinking about sustainability from the outset, renewable integration, how do you innovate construction material, sustainability as a metric, people do that as well. However, some companies are trying to kind of overcome it. They only talk about sustainability after it comes into UK, and you're like, well, that's actually not true, because what's happening to it when it's been built, so the circular thing. The big thing is public awareness, massive. and the life cycle assessment as well. So we're talking about, okay, when it comes off, how do you recycle it 20, 30, 40 years? This was much better. I think I gave the metrics of the AI tool to build the substation much better, so I got better at it towards the end. Nice picture of a Tesla coil that was taken in the lab, but yeah, that's me done. Hopefully that's given a good insight.
Thanks very much, Vidhi. So that was fascinating.
It's actually about kind of, I think Alexandra, that was, what is, I hope that you can kind of like enlighten us a little bit more. Because for me, universities seem to be these kind of like fantastic places of innovation, as we've seen this morning, and they come across as neutral catalyst, but we do know that they hold power. So how do you distinguish between kind of like meaningful community engagement and tokenistic community engagement? What are you actually measuring? Because it's obvious that marginalized groups, grassroots organizations, I've been working with 60 of them in the last 2 years, and they seem to still have this kind of imbalance of power. And universities hold money, they hold research, lived experience is still kind of like second class to academic experience. So I'm really interested, what are you measuring and how are you shifting this power?
Thanks, that's a very good question. So I think step one, as I said, is to get in a group of people from different areas. So yes, I work at the university, but I also run the Community Benefit Society. So my role is exactly that, to kind of try to mitigate with those issues and speak for the communities. And the way that I've solved it is to just ask the communities directly, hey, we've got this idea. We want to talk about how much it costs to heat the average home in the UK. And the way we're going to do that is we're going to have a winter warmer session. So we're going to come to your community, we're going to teach you how to make zero waste soup, and we're just going to talk about what difficulties you are having, but it's very much community led. So what we are measuring, we've got an impact scholar, and we've sat down with her, and we've essentially said, what do you suggest we measure? And she started out with a lot of different social metrics. And then we sat down with our engineers and they came up with a whole different group of metrics. And then they sat down with us and we came up with the economic metrics. And then we went back to the communities. And so we said, hey, out of this information, is any of this useful? And out of this data that we're getting, this is what we're getting. What are you getting in return? So I think it's a little bit about understanding that it's give and take, and we're not just going in to get data for our projects, we're not just going in so that we can publish papers, but we're trying to actually help while we are doing that. So I don't know if that answers your question, but...
Yeah, to some degree, because universities are still driven by research output and research outcomes. So, their priority will be financial to some degree, but communities need to kind of like see that benefit massively and transparently. And I don't know if I can see it right now, but obviously we're at very early stages and I'm still hopeful.
Just to add, I think we are moving away. Impact is very big for us. I mean, you said a statement that universities are rich. We're not. Research is actually done at loss. Research is funded at a loss, so it's very difficult. Oh, universities are moving towards impact. We're actually not measuring it on research anymore. We want to see output. We almost kind of think, and we're not just doing that on financial either. We almost look at, like, there is a socio-economic thing to that as well. We kind of think how does it impact the communities. So we are doing quite a lot on that. And it's not necessarily always driven by the pound or the dollar sign. I mean, maybe that's, but I do think that's genuinely true.
I also think there's quite a big transition with, I don't want to say younger scholars, but at least in my cohort, I've, as of 2 weeks ago, just submitted my PhD, and pretty much every single person I started with, we believe very, very strongly that yes, we have to put out the academic work, but we also want to have that social impact. So it's a lot of practice-based research, I think, that's kind of very popularized now. So I agree, I do think there's a change.
I mean, there's a tension as well, I think, in all of the, hearing from all of the talks about the energy transition and what, the energy transition is trying to achieve and the time frame within which that needs to be achieved, or if it's not done fast enough, what the other aspects of climate impacts, for example, need to be, we need to be resilient too. But I just wondered, David, you commented about the time frame of the kind of geothermal projects. Because clearly there's no silver bullet here to the energy transition. There's lots of different solutions, lots of different options, lots of different things that can be happening, probably all at the same time in lots of different contexts. But are there aspects of, how can things be accelerated? What maybe are the biggest blockers, especially when thinking about that community engagement? Because you mentioned that was no successful, I think you said no successful geothermal project has happened without public engagement. So, can that be rushed, that kind of meaningful engagement? Because there's a tension there, I think.
Yeah, any kind of project like that is a balance between, real world has to be done, has to make a profit. You've got a deadline versus you can't, in the real world, do everything that you want to do naturally. And so rushing sounds like a bad thing, but if you've got a project like that, if the time is reduced and you want to keep the scope the same, then you need to invest in people more to get a team together to progress the project on that sort of timeline. So it's always a balance, and I think in this project the people responsible for decarbonising the university heat network are facilities, right? So I guess what they would do is outsource that to an exploration company who does have the resources to do that. But the point I was trying to make is that the university really has to have a role to play in that, because the company are just a company, right? But there's so much more that can be done on the community engagement and all that sort of stuff, which I think is well within the university's sort of remit. And the company I don't think are going to do that. So we're going to have to talk to facilities and to get the academics involved, because we essentially doing the same thing. We can give it a sense check, and something the company are held to account. They make sure that drilling plans are feasible, that the work is feasible, and obviously they're not going to like that. But there is a big role for the university to play in keeping people honest and making sure that the social aspects of it that which are so important are actually done right.
Thank you. So we've got more questions. Yes, got a question at the back there.
My question is on solar energy. If you take the entire value chain of the solar energy, how clean is solar energy? I understand from the production of the cells, solar cells, in the Far East, is actually quite polluting, and then you transport, all the way from Far East to the Far West, which is UK, the entire chain. How do you take that into consideration? And second question on solar energy, UK. It's so hard to get the sun most of the year, there's no sun. And you enjoy the whatever sun, and the sun is very weak. How much energy can you generate from the solar energy? And third, in terms of implementation, our dear Miliband, are focused on having solar panel on the grass, beautiful grass, and the grass, die under the solar panel, besides creating a very ugly countryside. Isn't it better if Miliband and the government were to encourage the people to have the solar panel on the car parks and on the warehouse and in the city centre like Manchester by giving tax incentives? Like in Germany, they give tax incentives if your roof is green. Whatever it means, it can be you plant grassless plants and you use incentive such as lower council tax, to make the city greener. Thank you.
Thank you. Anybody want to touch solar energy? We haven't got any solar energy experts on the panel, I believe, but
There was a project that was trying to connect a solar panel in Morocco to UK.
right? And it just got binned about 6 months ago.
Yeah,
But no, I'm just saying, about if there is incentives, I don't think there's as much. Houses are not necessarily built to take them on their roof as well. You have to kind of think this is a retrofit. So how many houses of our houses are actually built to take solar panels as well is a big question. So yeah, not really an expert on it, but I think in terms of the adaptation of it, again, I don't know the circular economy of solar panels either, to be honest with you.
Yes, absolutely.
Which is that I work with different industrial clusters, and it's one of the common fallacies that we've all done. We've all looked out the train window and gone, why are they not putting solar panels? And very often I talk to industry companies with great big warehouses and things, and we think, why not cover it with solar panels? And just as you said, the roof isn't up to it, and it makes the capital cost too much, and they can't get the payback on it. So it's not quite as simple as just put it all on the roofs.
Same thing with heat pumps as well. Like your houses are leaky. Like, do you know what I mean? Like you're not going to get so yeah. Sorry, I'm not trying.
No. I mean, I think what it kind of illustrates. I don't know if anybody else in the room is a solar expert would like to comment on it. James, can we get a microphone over? Sorry. Yeah. Thank you.
So one thing about the location of the panels. Most of the large-scale solar panels, solar farms are located near to a substation. That's because of we do know that, the connectivity and the capacity. It would be too expensive to put solar farm in a place where the grid doesn't have the capacity. So that's why big solar farms go around an existing substation. Or there's a gas power station or a coal power station which is not functioning. So the substation is still there. So you can have the solar farm around there. The land-based, almost all the land-based solar farms are, they run different grades. Okay, so some of the farmland are not the highest, so it's kind of, they can't produce high yield crops from there. So it's kind of lower grade land. So that's where they're going to put solar farms. But then from a common man, if you look at the land, it looks like a nice farmland. But actually, there are different grades of farmland. But there's a big perception about by the look of the land and how it is and the actual productivity. So that's about the location. The tax incentives for the roof. I mean, the solar is so cheap now. Before we used to have feed-in tariffs and lots of incentives. Now we don't need incentives to actually have solar panels on the roof because it's so cheap. I mean, that's a good example. The UK government from 2010 onwards, different subsidies make that panels so cheap now.
You've done a great job there.
In terms of the solar radiation, I mean, yes, I mean, in the summer we have lots of sun. In the autumn and spring there is sufficient enough. I mean, the solar panels efficiency are so much better now. You can capture most of the different bandwidth of solar now, so you can have much more efficient. So I think even if it looks like more diffuse sunlight now, it does capture lots of sun these days. I mean, the newer solar panels, so even if it does work really well.
Thanks so much, Jace. So, yes, question from the lady at the front here.
Hi, Jenna Ashton from the School of Arts, Languages and Cultures. So I've got a very basic, boring question, which is probably my ignorance. Where are we up to in the UK with the upgrading of the grid then, given that it's all dying? So where is that in terms of the government's agenda?
The picture that I showed was 2030, the holistic network design. So that's the accelerated strategic transmission investment. That's 26 projects, and the deadline for that is 2030. But that's for those 26 projects. There's simultaneously other ones happening as well. This transition is going to happen for the next 50 years. We're not able, because we haven't even come to the domestic yet. The wires that go underneath your house are about 60, 70 years old. Do you know what I mean? They will need to get replaced at some point. If you all want a And a charging point, if it's a slow charger, fine, you're okay. They don't need any changes with you. If you want a fast charger, you need more juice in your house. The power needs to go up, so the cable needs to go up. It's happening, but we're talking the next 40, 50 years. What you want is the main links to the renewables to be done. That's when your bills come down. As soon as that happens, then you'll see lower bills, because that's the problem that we have, constraint costs, which you don't see. Constraint costs are where you can't actually transmit what you want. Silent killer was about $500 million or 600 million last year, which is basically you don't have enough to kind of you're generating great, but it can't get to your houses. So there's no point. Hopefully that answers.
I mean, it's such a big challenge that it's sort of similar to one of the points that was brought up in the materials session about not just thinking about, you know, how to provide the energy requirements. A small percentage of which is electricity at the moment in the UK. Most of it is non-electrified energy, but we're having to increase more things need to be electrified if that's going to kind of go down the low carbon route. But then, you know, how we can actually minimise the amount of energy we use as well, you know, through different ways of using energy or technology or efficiencies and so on. So I think it's quite interesting that this aspect of sustainability and asking those bigger questions about how are we using energy and why and so on, I think is really key. There's another question, yeah, please, at the front there.
Dr. Johnstone, you talked about the Manchester plan by 2040 to be running on geothermal energy. Is there built into that Greater Manchester plan to integrate the use of other renewable energies? Because you mentioned the challenges of, is it sufficient for the large scale? I know there was mention about how on the individual level for private buildings or whatnot, you can use heat pumps and solar panels to, boost your heating and whatever energy uses you have. But on the wider scale, is there a integration of other renewable energies to support or complement geothermal energy?
This is not my plan, right? So this really, what I showed was kind of a thought experiment, really. I'm sure that the Greater Manchester does have a plan, but I don't know what it is. What I was talking about is basically that the university campus has a certain power level which it needs to use, and that currently is all serviced by natural gas. And there are only a few things that will get up to that sort of scale, but there are a lot of other supplementary things. So individual buildings can use their own heat pumps, solar power, but none of those things individually. I mean, you would have to build, for 6 megawatts, you would have to build a wind tower in the middle of Manchester that had blades that were about 200 metres long. So that's not going to happen. So there are space constraints with what can be done. I think, not that I want to open the solar debate again, but I'm on the side of facilities, how do they decide? Because it's very difficult to be across all these different technologies. And you can see the people here, I know a bit about geothermal energy, but I don't know anything about solar or whatever. So at the top of government or Greater Manchester or the university, is there somebody who does understand all these things and other than just this costs this costs that, this costs this? So it's very difficult. I mean, and what I'm trying to say is this is a thought experiment. I'm saying that you could use deep geothermal energy potentially to get to a scale where you are covering a lot of the demand, and there are very few. We have a main sewer, for instance, that runs down Oxford Road, which you could take water at 15 degrees, take a couple of degrees out of that and use heat pumps. But there are very few other options. The other things, like heat from data centres, which people talk about, or solar or whatever, electrification maybe could do it, but you've got to have something which is going to give the base load, and I think geothermal is really one of the only options that you've got for that. Whether it's going to work or not, whether they'll go for it or not, I don't know.
If you want a bit more information on what options are, there's something called Future Energy Scenarios, FES. Future energy scenarios are done by
National Grid. They're usually done by the local DNOs as well. They'll give you an optioneering of what they see the energy is going to look like in the next 10, 20, 30 years. Hydrogen's involved in there as well, though I can assure you it's not necessarily anywhere close to what they consider your baseload. It's never going to be it. I like the word that you use, baseload. Always remember baseload. Renewable energy, how does that become baseload? You have a gas station which inertia, so it's there, it can take on a hit, it can take a knock. Renewables don't. So, yeah, sorry.
Can I just from the policy side, because I work with quite a lot of policymakers, and in terms of scoping, I think when we think of all these different technologies, solar, geothermal, wind, they're tools in our toolkit. I think we've now gotten to a point where we realize that it's a bit too late to sit down and plan an entire citywide infrastructure and wait until we have the money and the tech to do it. So really what we're doing is we're doing a collage of what we currently have. So I compare it to, I just got a new house and I hate my kitchen. I hate it, it's brown. I don't know who paints a kitchen brown. And I could go in, I don't know. I could go in and I could redo my entire kitchen, but it's gonna cost a lot of money, it's gonna cost a lot of time. And so what I did instead is I painted the walls. And it's temporary, but it fixes the solution. And then along later, I can then redo my kitchen. And I think that's kind of how we're treating renewables is we have solar panels now, let's put them in. Oh, now we have heat pumps, let's add those too. Now we've got batteries, let's add that as well. Because we really just we can't afford to wait another 50 years for a fully new everything.
So I think, you mentioned before about building communities of including researchers and including stakeholders and citizens. And I'm just thinking also, a remark was made earlier on in the keynote about, the difficult times that we're in at the moment. It's making, some of these conversations more challenging, more difficult. I wonder from your experience of the work that you've been doing recently, are there things that are being said, barriers being put in place in the way of some of these conversations that were not there, say, 12 months ago or 2 years ago? Like, are new things coming up that we need to be thinking about as the community who work on these things? Or are kind of or is it familiar? Are they kind of familiar themes that again, helping us to understand, in this challenge of the energy transition that keep emerging?
So I would say there are new challenges, but there are also old challenges. And what I mean by this is things are cyclical, trends are cyclical. And we saw this with certain terminology, like offsets, right? So offsets became really, really popular, and now they're the devil and we can't touch them because they're terrible and greenwashing. And now this is starting to occur with terms like net zero. So there's too many gaps, we shouldn't be doing it. And so we're so focused on the terminology that we're using that it's almost a distraction for what we're actually doing. The second one is, specifically in the UK, the current political environment fosters a lot of different conversations and a lot of distractions. So we're almost at some points deviating away from the climate crisis to focus on other things. But this is not new. This is something that has occurred before. So I think that with ground challenges like this is just kind of occurring consistently. And we just kind of have to keep on doing what we're doing in the background. I don't know if that...
Thank you. No, that's great. I think we are coming close to time and it's nearly lunch as well, and I kind of sense some hunger in the room. So I'm going to just leave it there and thank our speakers, but do please come and talk to our speakers who will be around. Thank you very much.